Hi folks, so in this video what we're going to do is we're going to complete the section A question of the 2010 DCG paper. As always in the section A there's going to be 4 questions, 1, 2, 3 and 4, and what you'll have to do then is you'll have to complete 3 of those problems, okay, and these can come from anywhere on the core syllabus, okay, any of the topics. So in these videos, as always, I'm going to go literally from A1 to A2 to A3 to A4. So starting with this one up here in the top left, which is actually a question here based on the topic of skew lines. So I'm just going to move my camera here and zoom in on that. Bring that into focus a little bit better. Okay. So you can see here it says the flight paths of 2 aircraft are represented by the 2 skew lines A, B and C, D. So what they're saying is 2 aircraft flew in these directions. 1 aircraft went in this direction, 1 aircraft went in this direction. What we have to do, and this is a common skew lines question, determine the projections of the shortest distance between the 2 lines. Okay, and then part B, determine and indicate the length of this shortest distance. Right. So there's 2 ways in general that this can come up, okay, well there is 3, but generally the 2 that most commonly come up are where we have to determine the shortest distance, and the other way it can often come up is where we have to determine the shortest horizontal distance. Now the method here is where we're going to actually create a plane. So what we're going to do that is I'm going to create a plane out of these lines. So the one I'm going to use is I'm going to go parallel to the line CD. So parallel to the line, or the flight path I should say, CD, I'm going to go parallel to the line CD from point B in elevation. So that line there that I've just drawn is parallel to the line CD there. So I'm just going to use a pen here. So that there is parallel. Now what we're going to do from A is we're going to project across a horizontal line from A. And that's going to give us a new point here now, and I'm going to call that point number, or letter, number, I'm going to say P. So point P. So, now that I have a point P in elevation, I now need to find a point P in my plan. So, projecting down, if P is in elevation up here, well in plan it has to be somewhere down there. And it's the same rules apply in the plan view. All we're going to do is, we're going to go parallel to the line CD, once again, from B. So parallel to the line CD, like we did in elevation, we're going to do the exact same. Parallel to the line CD from B. I'll project this up, and that there is now going to give us the plan view of point P. Now what's important about that is P connects back to A, so I'm going to connect that back to A there. But that line there specifically is actually now a true length line. I'm just going to, for neatness purposes in the video, we're about the excess there. Okay, so that there now is a true length line from P to A in plan. Why is it a true length? The reason this line is a true length is because the line P to A in elevation is a horizontal line. It is parallel with the XY line. Therefore, when we're looking directly down on top of it in the plan view, that line will now become a true length. And we know then, if we look along a true length, because we've created a plane here, okay, we've created a plane PB. If we look along a true length on that plane, we will see that plane then as an edge view. But more importantly, we'll see these 2 flight paths, okay, and they will appear parallel to one another. So how do we do that? What we're going to do is we're going to set up an X1, Y1 perpendicular to our true length line. So you'll see here X1, Y1, so there you go. I'm going to rotate my set square. I actually have to move my mouse, or move my set square around a little bit. Just keep it nice and neat. Here we go. And inside here I'm going to have an X1, Y1. So I'm going to label that X1, Y1. Okay, now I'm going to project out all the points. And all the points will project out parallel to the true length, perpendicular to the X1, Y1. So C will project out, B will project out, D projects out, and A will project out. Okay, and the rule of thumb here is we have projected from the plan, we will now take our heights from the elevation. Now to take accurate heights, what I often like to do is I line C in plan up with C in elevation. Just draw in the elevation line there, the vertical line. Just means that I'm going to get the accurate heights. So D lines up with D, B lines up with B, and I'm just drawing in the elevation line. So I'm going to start off with A up here at the top. So I'm going to take the distance from the XY line up to A, taking that distance on my compass. Happy with that. Come down to A in plan, follow it out, and I mark it out on the X1, Y1. What I've now located here is A1. Okay, likewise then, I'm just going to do D because it seems to be a similar height, slightly, just slightly. There we go. Now I'm going to do it for D, follow D down, where D projects out from the X1, Y1, mark D1. Okay, now what we're going to do is we're going to take the heights for B and C. So, switching up here, getting the height for B, follow B out from the X1, Y1, mark it off, and likewise from C, take the height for C, follow C out, and we'll mark it off. Okay, so I've now found B1 and C1. Now these questions are often a true test of our accuracy. So what I often like to do here, I have to now connect AB, so A1 connects to B1 and C1 connects to D1. And I'm going to connect those up, but before I draw them in, I might draw it in lightly first. I like to test then because the line C to D should be parallel. We'll see how close we are. Not too bad, probably half a mil out in one of them, but that's okay. So I like to use sliding set squares to do this part. So there's my lines, okay, and they're appearing as if they're parallel. Now in reality they're going at different angles to one another, but as we look down at them, okay, it's like they're like this, but it's nearly as we look down top of them, okay, or sorry, in the elevation view, this is an auxiliary elevation, it's nearly like they're appearing parallel, okay. So what we have to do here is now we have to get the shortest horizontal distance. So how do we do that? All that means is we're going to now look perpendicular to them and we will be able to see the shortest horizontal distance between them. Okay? So to do that, all I'm going to do now is I'm going to set up a second auxiliary in x2, y2, and I take my measurements from the previous xy line back. So I'm going to set up my x2, y2 right here. The x2, y2 is going to be parallel because we're now looking in this direction. Okay, so it's going to be set up parallel in line with the lines, where we're going to project out perpendicular. So I'm going to call that there x2, y2. Now I'm going to project out the 4 points. So C1 will project out, B1, D1, and A1. Okay, they've all projected out there. Now I just have to locate them. And now I'm going to take them from my distances from the previous xy line back. So I'm going to take them from the x1, y1 back. Now as you can see, there is quite a large distance there. And based on the space on my sheet, okay, it doesn't look, if you see here, let's say I take the distance for letter C there. So if I take the distance from the x1, y1 back to C, you can see here from C1, I go out to the x2, y2. You can see it's kind of going off the question down here. Okay, so how do I do that? What I can do is I can eliminate the space between the x1, y1 and the actual points here. So what I'm going to do is I'm going to set up a datum line. So there's my x1, y1, parallel to the x1, y1. I'll project it across. I'm going to set up a datum line. I think about there is appropriate. I'm just going to put it in as a dotted line there, like that. And I'm just going to write in the word datum. What that does is it allows us to eliminate this space, but the space that we've eliminated is the same for every one of these 4 points, A, B, C, and D. So now I'm going to take the distances. I'm going to start with A and just work my way down. So starting with A, there's the distance for A. Now I come out to A1, follow it out to the x2, y2, mark it. Now I'm going to do the same for D. There's D, followed out to D1, off the x2, y2, mark it. And I'm going to do the same for B. Small here now, this one. Just make sure your accuracy is right. Follow out to B1 onto the x2, y2. And then finally onto C. And from C1 out to the x2, y2, mark it out. Now once again, just going to label these. So these are now going to be A2, D2, B2, and C2. So I'm going to join those up. So C2 is going to connect to D2, A2 is going to connect to B2. And at the point where they actually intersect, that is going to reveal to us the shortest distance. Okay, I'm just going to write in there, shortest distance. Now, how do I show that though? I have to project it back along my views. So working back to our first auxiliary, the auxiliary elevation from the x1, y1, projecting backwards now. I'm going to take from where they cross each other all the way back, and inside there, that is our shortest distance. Okay, now this is the point where it hits on the line AB, this is the point where it hits on the line CD. Now I'm going to project them back to my plan view. Just projecting back. So this point here is on the line CD, and this one is on the line AB. You can see here they're literally hitting right there. It's very close now. Maybe like they're appearing like a vertical line. I say a vertical line, that's how they're appearing in the plan. Okay, and now we want to project them up to the elevation. So we have to find them in all views. So this point here is on AB. So that's that point there. And the one that's on CD seems to be on the same line. So it's going up like that. So it's nearly actually like they're appearing. I'll hit that. So that's there. There we go. That is our shortest distance, okay, in between them. So right in there, that is, I suppose, our shortest distance. Now, that's part number 1 done. Now what we're going to do is part number B, determine and indicate the length of this shortest distance, okay? Now this is really, really easy, but the only way we can see the length of this shortest distance is when we're going to actually see the two lines, the two skew lines, when they are parallel. So the actual shortest distance between them, if I was to extend this line out here, and it tells me to indicate it, so I'm just going to extend that out, and the shortest distance would be that little gap in there. Okay, so determine and indicate the length of this shortest distance. So if I was to measure it, it looks like there it's about 4 millimeters to me. Now we're not given a scale, but on my sheet I'm just saying 4 millimeters. So there we have it, guys. That there is the first question, question A1 completed, based on the topic of skew lines. Now what we're going to do is we're going to move down to the question underneath the page, or underneath this one. So just going to slide this down. And there we go. Now what we're going to do is we're going to complete this question here based on the topic of axonometric projection. Okay? So in this question, it says here a pair of bookends, each of which incorporates a globe, okay, and some books are shown in the 3D graphic below. A set of isometric axes is shown on the right, and the elevation and plan of a bookend which incorporates a globe have been positioned as shown. So we've got the elevation view here, we've got the plan view here. Okay, draw the axonometric projection of the bookend. Right, so essentially what they're kind of showing to us here is, if you think of the bookends, and we can obviously see the books, but really all we're focused on here is this kind of black portion here, which is kind of like in the shape of an L, and we've obviously got the globe. And you can see here, that's kind of the black portion, and there's our globe. And in the plan view, that's the top surface there. So this kind of surface there would be this line in the elevation. And then this rectangle here, well, that's this guy. And then we have the globe. So what we want to do now is we're going to try and complete this. So in axonometric projection, and specifically isometric axes, all these lines, the z-axis should be at 30 degrees, the x-axis should be at 30 degrees, and the y-axis is vertical. So if I'm using my 30 degree set square, yeah, you can see there that's set up perfectly. So I'm going to start off by creating the actual bookend before I put in the globe. So to do that, I'm going to project on my points. Okay, there's a point here, that'll come down, point here, and this point has come down, this has come down. So it's going to project down parallel to the z-axis at 30 degrees, and this one. Now, after they have all projected down, I now need to project the points up from the plan. So these ones are just going to project upwards parallel to the y-axis. I'm going to start with this face here, okay, where I'm going to see the L, and then there's also a face at the opposite side, but I'm just going to start with this one. So this point here is going to go upwards, this point upwards, and the other point that I need to go up is this one. It's going to go up as far as there. Okay, so there guys, just have to focus the camera there. Now what we want to find, okay, if I was to use labels just for demonstration purposes in this first question, let's say I had this point here and that's number 1, number 2, this point down here is number 3, 4, 5 and 6. So if I was to label that side face, okay, just one side down here, well, where would 1 and 2 be? Well, 1 is at the top, 2 is at the top, so there's 1, there's 2, 1, 2, okay. Then underneath 2 we have 3 as it goes down, so 3 is down here, okay, it's in the same place underneath 2. Then we have 4 all the way at the front, and what's underneath 4? 5, as we look down top of it. And what number is underneath 1? 6. So you can see 1 and 6 is associated with this point, 2 and 3 here, and 4 and 5. So now if I actually want to find them, it's simply a case of kind of following the map that I projected. So if I want to find 1, where 1 goes down and 1 goes up, there's 1. Where 2 goes up, 2 comes down, there's 2. Okay, and I can repeat that sequence. Number 3 goes up, it's on the same line. Okay, and number 4 will come up to here, 5 there, and then the last one is number 6, and 6 is actually probably going to be right there. Okay, so there's my points. Now all I have to do is connect them up, and they should actually meet up, if I'm accurate, at a 30-degree angle, and they do. 30 degrees, 30 degrees, and these two at the top, 30 degrees. Now, for demonstration purposes today, I'm just going to heavy it in with a marker. So this is my side face. Trying to be as neat and tidy as I possibly can. So there's the side face. And now I have to obviously make that whole object before I put in the globe. So the face is now going to go in this direction, and that's going to end over here. So this line will come up, and that's where that face is going to end. So I'm going to heavy that in. Heavy this bit in here. And as we work our way along, it's the same at the top. So the other points that I need to bring up now are this one, which is already up there, and this one. And at the very tip top then, I'm going to get a point right there. It's going to go back. Okay, and then just to actually show it before I heavy in the globe, that there would actually be the other face and this face. Now I'm not going to heavy those in just yet. I'm just going to adjust my light in there. Apologies. Now I'm not going to heavy in those just yet because I'm going to put in the globe, and the globe is going to get in the way of some of that information there. So how do we do the globe? Well, the globe is completed by identifying the center point. So it's the same method. Now what we have to understand is, even though we're doing a 3D view here, is in this view, which is the elevation, we're seeing the globe as a circle, and in this view in the plan we're also seeing the globe as a circle. Now in the 3D view, or the axonometric, the axonometric, we're still going to see, even though it's a sphere, we're still going to see it as a circle. So I projected down the center is somewhere along that line. I now need to project up the center point from the plan to locate its exact position. And you'll see then that when this line comes up and this line comes down, they're actually meeting right in here, right in that point right there. Now how do I draw it in? Well, quite easy. All I have to do is take the measurement from the elevation or the plan. because it'll be the exact same size. So all I do is I take the radius of the globe from there, and I'm going to draw it in here. I'm going to start off, I'm going to draw it in with a pencil first, and then I'll heavy it in. You can see now why I didn't heavy in all my details. So there's my globe. You can see it in there kind of lightly. Now I'm going to switch out to my marker. I'll try and do this as neatly as I possibly can without slipping. Okay, so put my compass in there. Pencil in here. Okay, there we have our globe. Now, I'm going to finish off final details. So the edge here, I can see now how far it goes down. Same here at the front, how far it goes across. And then I would have obviously where the vertical surface meets the horizontal surface, identifying that edge there as well. And I do not have to put in hidden detail in the axonometric. Okay, so there you have it, guys. That there is the second question here based on the topic of axonometric projection. Now what we're going to do is we're going to move up to the top right of the page where we're going to complete a question based on the topic of conics. So, sliding up here, let's move this across. Right, zoom in slightly there. There we go. So this question here is based around the principle of a parabola. Okay, so it says here, A3, a parabolic curve is often used in design of racing tracks. The drawing on the right shows the axis, and our axis line is this line. Our directrix, DD, this is our directrix, and focus of a parabola, and you can see our focus here. Part A, locate the vertex and draw a portion of the curve. And then it says part B, draw a tangent to the curve at a point 45 millimeters from the focus. So, when we're drawing a parabola, an ellipse, okay, or a hyperbola, what we need to know is the eccentricity. Now, what's helpful about a parabola is the eccentricity is always 1:1, okay, because it is a parabolic curve, okay. Now, how do we draw on the eccentricity? Well, the eccentricity line comes from the directrix and the axis where the two of them meet, right here at this point. And because our parabola's eccentricity is 1:1, well, that line is always going to be for a parabola at 45 degrees to the axis. So, from the directrix where it hits the axis, from here, I'm going to do a 45 degree line. Now, for today's demonstration, I'm going to put it in green. And that line there is the line of eccentricity. So I'm just going to write L-O-E. Okay, line of eccentricity. Now, that's the first thing. How do we find then the vertex? Well, the vertex is always found the same way. From the focus, we're going to project back at 45 degrees. And where it hits the line of eccentricity right here, we're going to drop it down parallel to our directrix or perpendicular to our axis, however you want to say it. And at that point right there, that is going to be the vertex of our parabola. So, V. Now, how do we draw it? So, from the focus, we have a line that is now going to be called the latus rectum. Okay? This is going to help us draw it. So from the focus, I'm going to do a line up and down like this. That line there, just for demonstration purposes today, I'm going to write this in. It is called the latus rectum. Okay. Now, the method of how we actually complete the parabola is we're going to do a series of ordinates. So in between the vertex and the focus is quite a small gap. I'm simply going to do a line like this, up and down, and it only has to go up until it hits the line of eccentricity. I just want to make sure below the axis down here, I want to make the line roughly the same length. Now I'm going to do a series of others, and they can be spaced as however you want. You can space them equally or you can do them randomly. I'll actually do them, I'm just thinking here, I'm going to do one at 10, one at 20, one at 30, and I'm going to do one other one at 35. That's where I'm going to stop. Okay, so all I have to do, same thing, like I did here, I'm going to do a line up until it hits the line of eccentricity, but go down roughly the same length. So each one I'll probably just get a little bit longer. And then here. Now, the method then of how we actually complete the parabola is this. From where each one of these points, okay, hits the line of eccentricity for my ordinates, this was ordinate number 1, 2, 3, 4 and 5. From ordinate number 1, okay, I'm going to go across to the right to hit the latus rectum, and it goes across. However, on this side, it's going to go to the left. Likewise with this one. Likewise with this one. And likewise with this one up here. And it's gone into my text a little bit, but that's fine. Okay, so that's the method. Now we're going to plot our points. Now the vertex is always a point on our parabolic curve. Okay, and where our focal lines, or our lattice rectum line, intersects with the line of eccentricity. So you'll see here the lattice rectum line. And where that intersects with the line of eccentricity is actually also going to give me a point on my parabolic curve. Now how do I find a series of others? Okay, so I'm going to find the one at the opposite side here. So I'm going to put my compass point on the focus. I'm going to adjust the compass until it hits that point. So I'm going to find that one at the opposite side just to have it done. Okay, so I can locate that point on my curve. Now I want to find the others. So the method is, I'm going to start with the top one. Okay, put my focus up here. Sorry, the bell there. I'm going to, for this outside line, I want to find the parabolic points on this outside ordinate. So I put my compass on the focus and I put the pencil from where it went up to the line of eccentricity and across. I'm going to put my pencil up to that height there. And I'm going to swing it across until it cuts the ordinate. Swap it around and get that distance at the opposite side. Now I'm going to go down to the second one. And I continue in that sequence. I find the second one. Down to the next one. Make sure I'm taking the accurate height. There we go. And there we go. And then this one here. And there we go. And now this one here just happens to be on the inside. I'm going to adjust the compass there until it gets to the point. Happy with that, and I just turn it the other way. And I get one there and there. And all we do then is look, really easy. I'm going to mark my points with a little black marker. And that there is going to help me produce my parabolic curve. Now before I sketch it in with the marker, I'm going to use the pencil. I'm going to try and make this flow as smoothly as possible. So you want to go between the points here, and then it's going to start moving away from the line of eccentricity. Right, so there we have our parabolic curve. As best I can, I'm going to using the marker. So that's my parabolic curve on the top half. Trying to get it on the bottom half now. Okay, so there we have our parabolic curve. That is the first part. Locate the vertex and draw a portion of the curve. So now what we're going to do is part B, draw a tangent curve at a point 45 millimeters from the focus. Okay, so easiest way we can do this is we need to set up 45 millimeters on our compass. Okay, so I'm going to get 45 millimeters on my compass. So I'm just going to bring this up here and I'm going to put my compass point on the 45 centimeter mark. And I'm going to mark out 45 millimeters. So that would be 10, 20, 30, 40, 45. So at that point there is 45 millimeters. So it says here, draw a tangent curve at a point 45 millimeters from the focus. So from the focus, I'm going to swing an arc. And this arc that I've just done there is 45 millimeters away and is touching right there. That point there is 45 millimeters away from the focus. Now there's two ways that we can get, or there's a couple of ways we can get tangents to our parabolic curve. I'll show you two ways here. The first way that I like, and it's my kind of favourite method, is whereby what we're going to do is we are going to join the point where it obviously touches, which is I suppose our point of contact. I'm going to connect that point back here. I'll actually put this one in red. So I'm going to join this guy back there like this to the focus. And what do I do then? All I need to do from there is I'm going to go perpendicular to that line until it hits the directrix. So with this line set up, I'm now going to rotate my set square so it's perpendicular. Like that. I've now got a perpendicular angle. I'm going to do a line like this. And you can see at this point here, where it touches the directrix, well, that is another point on my tangent. So now that I have this point, plus the point of contact, to draw on my tangent, I simply connect them. And there we go. That is our tangent. Okay? So that's the method that I prefer. Now the other method you could do is you could also connect this point to the focus, and then from here, let's do it really quickly. I could do a line across like this, and you can see the angle created between this line and the point of contact to the focus. So that line in there connected to here. If I bisect that angle there, well, my bisector should also give me my tangent. Okay, I'm not going to do that method in this video. I prefer the method where I join the point of contact to the focus and I go perpendicular. So that little angle in there is perpendicular. Okay, and where that comes across and it actually hits the directrix, well, that is a point on my tangent. I can connect that then to here, which is the point of contact for our tangent. As I said, then you could also do this one where you connect it then to the focus, join a line in line with the axis, okay, cross then to hit the directrix and bisect that angle. Okay, that is another way it works. But there you have it, guys. That there is the second question, or sorry, the third question done on our page. So now what we're going to do is we're going to move down to the bottom question here, which is based on the topic of the oblique plane. So A4. So in completing this question, what we're going to do is, it says the 3D graphic below shows the design of a display box for fruit. The box consists of a regular hexagonal prism which has been cut as shown. So you can see here we have the kind of, I suppose, the elevation of the original prism. Okay, we'd see the plan view of it here, and you can see obviously in the 3D pictorial here we can see how it has actually been cut by this oblique plane VTH. It's like a sheet came along and just sliced across it. Okay, it says here the drawing on the right shows how the prism is cut to form the sloping surface. Part A, draw the elevation of the prism when cut by the oblique plane. So to draw this, what we're actually going to use is the principle of horizontal cuts in relation to our oblique plane. So in the plan, you'll actually see we've kind of got 6 points that we have to find if I just kind of use this guy as a reference. Okay, I have a point down here, I have a point here. They are at the same height. Okay, they are both the same height up from the ground. Okay, then I've got these 2 points, which once again are at the same height as each other, and the 2 points at the top, which are at the same height as one another. Okay, so what we're going to do to get these points is the 2 points on the ground, which are these two. Okay, just based on the graphic, these are the ones. So what we're going to do is parallel to the horizontal trace. So we're going to project the 2 points parallel to the horizontal trace, like that. I'm also just going to set up these ones at the same time, the 2 in the middle, and then here's the 2 at the top. Okay, just setting them up like that. Now what I'm going to do is, where they hit the XY line, I'm going to project them up until they hit the vertical trace. I'm going to project this one up as well, and I'll have this one up. Now, for the 2 points that are on the ground, or sorry, not the ground, but I suppose our lowest 2 points, this one and this one, which is here and here. As they project up and go across, or sorry, go upwards and hit the vertical trace, I'm now going to project horizontally across. Okay, because this is a horizontal cutting plane. And what that's actually going to identify to me is whereby it's going to cut through. So if you follow this one up, well, that's going to cut right there. And if you were to follow this one up, well, that one's going to cut right there. Okay, so if I was to actually draw that in, I could now heavy that bit in and heavy that bit in. This is probably where the marker is not working great for me. What I'll have to do, so that there is now my front face. So now what I have to find is the second 2 points. So it's the same method. Here's the second 2 points, follow them up where they hit the vertical trace, project across, and that's actually going to identify this one. So there's one. If I follow it up, that's where that one is. And if I follow this one up, that's where that one is. Okay, so at that point there, I know they connect on the outside, so I'm simply just going to line them up with my pencil before I draw with the marker. Just help me stopping the marker bleeding. Okay, and sorry there guys, just have to move a second. Lights are just censored in here. And now I'm going to find the top 2 points. So the top 2 points, same method, where these two went parallel up to the horizontal trace because I'm using the horizontal cutting method, going up, hits the vertical trace, line across, and that's going to identify this point and this point. Okay, I can actually heavy that in, because that's the top surface. And now that will simply connect down as well. Okay, we'll heavy that in. Okay, and that there is our cut solid. I'll heavy this bit in here. So always in DCG you would have to, now the hidden detail is kind of already put in for us. If you wanted, you could, I suppose. It's me just, I suppose, making sure leaving nothing to doubt. Okay, so there we have it. That there is part A done. Quite easy. Okay. Draw the elevation of the prism when cut by the oblique plane. Now the plan is the exact same, even though the surface has been cut and we're seeing this cut surface here. Okay, in the plan it still looks like a hexagon. Now part B, determine and indicate in degrees the inclination of the cut surface to the horizontal plane. Okay, so what they're basically asking us here to do is they want us to draw an auxiliary view of the object that will show the cut surface as an edge view. Okay, now there's a couple of ways you could probably go about explaining this, but the easiest way I think is actually to identify the oblique plane as an edge view. So how do we do that? So what we're going to do is we're going to look along the horizontal trace. The horizontal trace is on the ground because that is where it is intersecting the horizontal plane. This oblique plane is cutting through, and where it intersects the horizontal plane, it leaves behind a trace called the horizontal trace. Now, because that is on the ground, it is a true length. So, what we're going to do is we're going to project this out a little bit here, just a little bit, and then we're going to set up an auxiliary view because we're looking along it, we're projecting, and we're going to see the horizontal trace as a point view. I'll bring it out to about here. Okay, now that there is my x1, y1. Now, I've got this point right here. That there, that point that I've just labelled, is a point view of HT, the horizontal trace. Okay, so because we're seeing the horizontal trace as a point now, it's like we're seeing the line, it's like we're seeing a line as a point for all the world. Okay, I now have to get a point on my vertical trace where then I will actually see the oblique plane as an edge view. Okay, and that essentially is going to be our answer. Okay, so how do I do that? Well, what I can do is I actually have a height here because this is on the ground. I have the height for a point that is up to the oblique, up to the vertical trace. So I could actually use this one here as my guide. So I'm going to project that out parallel to the horizontal trace. I know the line is already there, but I'm just going to use the sliding set squares method. There's my point. So that will go up there. And how do I find that? Well, what I do is I'm taking this height here from there to the XY line up to there. So that little height there, I'm going to get my compass. I'm going to mark that. So I took that height just there. I'm going to come up along here to the x1, y1 and mark that. Okay, and what that is going to give me is a point on my vertical trace. This point here is representing the horizontal trace, and then the vertical trace is there. So that line there is I suppose our edge view of our oblique plane. So that there is our edge view of oblique plane. Now, that's our object. Okay, if we actually wanted to draw the object in, this could have actually, I suppose, helped us identify these cut heights here as well. There's lots of ways of going about it. So if I was actually to project that up, now what does it say? Determine and indicate in degrees. Apologies. Now that's actually my cut surface, but before I do that, just for, I suppose, demonstration purposes, I'm going to project this up. So that would have gone up. I'll bring up the other points here as well. Now they're the two at the middle height. These are the two at the top height. And it's like, I'll actually extend this on because it would have cut through the whole object, so we would have actually gone like that. Okay, so now how do I draw on the object? Now we're going to imagine that the prism was in full height here, so because before it had been cut, so I'm going to take the height, project from the plan, take our heights from the elevation, so I'm going to take the height of the overall prism, which would have been all the way up to here, the red line. I'm going to take that height, and I'm going to mark it up along one of these lines. You can mark it on 3 of them if you want. They should all meet at the same height. Okay, there you go. They'll all join across, and essentially that would actually be our prism. But I'm just going to heavy in the bit that we would see. So this is like the object that we would see. Okay, and that there is the area that has been cut. All this area up here, that's the oblique plane cutting through our solid. Therefore, that is the area where we're seeing kind of this like, I suppose, sloping cut surface. Okay, but what they've specifically asked us though was determine the indicating degrees inclination of the cut surface. Here's our cut surface identified by the edge view of the oblique plane in regards to the horizontal plane. Our horizontal plane here is the XY line. So all we do is we get our protractor and make sure I'm measuring accurately now. And I'm getting there 10, 20, 30, 40, 41, 2, 3, it's about 43.5, 44, I'll say 44 degrees, we'll round up. So I'm going to say there 44 degrees. And there, into there. Okay? And yeah, there we have it guys. So I'm just going to zoom out there now. And just orientate that a little bit better. So we're back looking at the whole thing. So there we have it guys, that there was the 2010 Leave Insert Section A questions, okay? 4 questions on the page, as always you only have to do 3. Now they were kind of nice questions, you had an oblique plane, axonometric, you had a conics question and a skew lines, okay? Those kind of questions often come up in the short answer questions, alright? So 2010 done there, hope you found that helpful, okay.